So again, good afternoon. Our group will be discussing about cooling tower. For the introduction, I'm giving the floor to Harold Panganaro.
So, good afternoon to one and all, and we are going to report about the cooling tower. So, first, understand what is a cooling tower. Here is the principle behind the cooling tower. So when a warm liquid is brought into an unsaturated gas, a part of the liquid is vaporized and liquid temperature drops. So with this observation, the people would like to use this observation to develop equipment that would utilize the enthalpy of the gas and so that the liquid temperature would drop and the liquid would vaporize. So this was from the unit operations. So what is a cooling tower? A cooling tower, in principle, is a special kind of tower that conserves cooling water by allowing the cooled water to be reused many times. So we have background about cooling towers since we have ChE 152, which is transfer operations 1, so we know what would a cooling tower look like. Next, so what are the costs of heat transfer during the cooling tower operation? First, there is latent heat transfer, and then there is sensible heat transfer. So, latent heat transfer occurs when water is vaporized, when small portions of water is vaporized into the air. So, it accounts for 80% of the heat transfer in the cooling tower operation. Next is the sensible heat transfer, which is to the difference in temperature between the water and the air. So it accounts for 20% of the tower operation. Next, so what are the factors affecting heat removal? First, we have air moisture content, then we have the air temperature. So in air moisture content, we have moisture, we all know that is the water content of a certain material. So when we have air moisture content, means that the air moisture content in the air. So this affects the heat transfer, since the amount of water that would vaporize would be limited since there is already water inside the air. Next is air temperature. So when we have air temperature, when there is low air temperature, the transfer of heat is also minimal. If there is high air temperature, then we can use the high temperature to transfer the heat from the air into the water. Next, evaporation of water into air is brought by the difference between the vapor pressure and the vapor pressure of the air wet bulb temperature. So this difference between the discharge temperature of the water as well as the wet bulb temperature is called the approach. So, there. Since the approach is very important, is an important factor to consider so that we have an estimate of how much the heat transfer would be into the liquid. So we should consider the factors affecting the magnitude of the approach. So the magnitude of the approach is affected by the air to water contact time, the amount of field surface, and the breakup of water into droplets. So in practical purposes, the approach is no more closer than 0.8 degrees Celsius and 5 or 5 degrees Fahrenheit.
So thank you, Harold. There are two general types of cooling tower. The first one is the natural draft, and the second one is the mechanical draft. So there are different parameters to consider in order to differentiate these two general types of cooling tower. Number one is the cause of air movement. For a natural draft cooling tower, the main cause of air movement is the density gradient. or the differences in the density of the cool inlet air and the warm exit air. While for the mechanical draft, the mechanical fans are used in order to cause the air movement inside the tower. So, another parameter is the tower size requirement. For natural draft, the size of the tower is dependent on the value of the approach. So, generally, low approach means a larger cooling tower size. For mechanical draft cooling tower, this parameter is dependent on dependent on this 6. Number 1 is the cooling range. Number 2 is the approach, quantity of water, wet bulb temperature, air velocity, and the tower height. So here is the comparison of the advantages between natural draft and mechanical draft. For natural draft, it has lower power requirement because there is no fan that is needed to operate. And then the quantity of cooling water that is being brought back into the cooling tower can be decreased if the wet bulb temperature of the air is lower than the required cold water. For the mechanical draft, it is the versatility on the location. Why is that so? Because it can be used on areas where wet bulb temperature of air is high and exists over a long period of time. And it can be used in areas where power costs are minimal and there is the availability of maintenance crews. And also, an advantage of using mechanical draft is there is this maximization of heat transfer because the fans cause an increased contact time between the water and the air. And cooling rates can be controlled by adjusting fan speed and the fan diameter and the length. So, the disadvantages are, for natural draft, there is this provision to supply cold water to the tower. A supplementation of cold water to the tower is needed in order to lower the cold water temperature. Also, it requires large size of the tower in order to attain the same cooling quantity as compared to mechanical draft. For the mechanical draft cooling tower, the disadvantages are, number 1, it has additional costs. Why? Because there is a need to maintain fans and pumps. Also, there is a need to recirculate the humid vapor back to the incoming air for a forced draft cooling tower. That is only for if the mechanical draft cooling tower is a forced draft one. So to explain more about natural draft cooling tower, we have Denise doing.
There are two types of natural draft cooling tower. The applications of natural cooling draft towers are an HVAC, heating, ventilating, and air conditioning. Cooling tower is a subdivision, this allowing heat from a chiller. Water-cooled chillers are generally more energy effective than air-cooled chillers due to the heat refusal to tower water at or near wet bulb temperatures. Large office buildings, hospitals, and schools typically use one or more cooling towers as part of their air conditioning systems. Generally, industrial cooling towers are much larger than HVAC towers. Industrial cooling towers can be used to eliminate heat from various sources such as machinery or heated process materials. The primary use of large industrial cooling towers is to remove the heat absorbed in the circulating cooling water system used in power plants, petroleum, refineries, petrochemical plants, and etc. There are two types of natural cooling towers. First is the natural draft atmospheric cooling tower and the hyperbolic cooling tower. First, natural draft atmospheric cooling tower, the mechanism is that the wind velocity activates the heating transfer of the process. Also, wind velocity determines the airflow in the cooling cooling tower. If heat process drops, there will be loss of air flow. Natural draft atmospheric cooling tower are used for low cooling loads. They are designed for leaving tower 4 to 5 degrees Fahrenheit lower than the wet bulb temperature of the entire air. Natural draft atmospheric cooling tower have drift eliminators to stop the water loss when wind velocity surges. Natural draft atmospheric cooling tower are very cost effective. They have low capital investment and they are operated in minimal expenses. Natural draft atmospheric cooling tower have a 30 to 55 degrees efficiency. However, its efficiency fluctuates because it is dependent to the wind velocity. Also, natural draft cooling tower is only the airflow only moves in a cross-flow manner. So it is where the wind blows horizontally. This is the mechanism inside natural draft atmospheric cooling tower. The wind blows, the air comes from the other side and it comes from the next. Next is the natural draft hyperbolic cooling tower. This is a picture of a hyperbolic tower. The mechanism is that the temperature differences inside and outside the tower changes the density of air, therefore producing the airflow in the tower. It has a large top or chimney. The cross section is enlarged at the top of the tower, so that kinetic energy is converted into pressure energy, then assists the dispelling humid air to the atmosphere. Hyperbolic cooling towers are associated with power plant operation because its efficiency is linked to relative humidity and temperature of the outside air. Hyperbolic cooling towers are used for flows in excess of 500,000 gallons per minute. Hyperbolic cooling towers, the airflow can be cross-flow or counter-flow. Unlike in the atmospheric, the flow only flows cross-flow. In cross-flow design in hyperbolic tower, airflow rates are higher, therefore promoting the improved air-water contact. It will operate at a lower head loss as the same capacity as the counterflow in the hyperbolic. In the counterflow design, evaporative heat transfer is more efficient. Therefore, because water is always be in contact with the coolest air and minimum amount of film is required. This is the mechanism inside the natural draft hyperbolic cooling tower. The most general accepted theory of cooling tower heat transfer process is that of Merkel.